Welcome to a Regents Physics quiz review. This is going to be for circuit electricity, circuit basics, all our equations before we really get into series and parallel circuits. So we're going to do our about 12 examples here, a mix of calculations and conceptual questions. So example number 1 here, we have a radio operating at 3 volts in a constant temperature, draws a current of 1.8 times 10 to the negative fourth ampere. Was the resistance of the radio circuit? So like we've been doing in class, the way to go about these questions is to pick out what we have in the question and then match that up with an equation on the reference table. So each of these values is going to have a variable on the reference table. You're going to flip to electricity, and you're going to go to the right side of that page and figure out what variable they are talking about, then match those variables with an equation on the left side of the electricity portion of the reference table. So let's see what we have here. We have that the radio is operating at 3 volts. So we know that volts is going to be the same thing as potential difference, or V on the reference table. So we're going to plug in here and say that V is equal to 3 volts, and that unit is just V for voltage. It says a constant temperature, so the temperature is not changing my resistance at all. And it says that we are drawing a current of 1.8 times 10 to the negative fourth ampere. So look on the reference table again. What is current? That is I. So I is equal to 1.8 times 10 to the negative fourth amperes. And then we are being asked finally at the end here, what is the resistance of the radio circuit? What is resistance on the reference table? That is R. So this is what we are looking for. All right, so from here, we are now going to pick out an equation that involves resistance, potential difference, and current. So you look on the left side of the reference table at all your equations. We see here that the equation for this, we're looking for R. There are 2 equations with R, but there's only one with potential difference and current. And this equation is Ohm's law. So we have R equals V over I, which again, resistance equals potential difference over my current. So all I'm going to do now is just plug in my numbers, and I should end up with the resistance for this scenario. So R is what I'm looking for, so that stays as is. V is 3 volts over the current, which is 1.8 times 10 to the negative fourth, and that is amperes. Now all you're going to do is plug this into your calculator, make sure that you have the scientific notation plugged in correctly, and you're going to do 3 divided by 1.8 times 10 to the negative fourth. And you're going to end up with a value here for resistance as 16,666.67 ohms. In scientific notation, if it ends up being a multiple choice question, we are then going to end up making this around 1.7 times 10 to the, we have 1, 2, 3, 4, 5 before the decimal, minus 1 from that, so times 10 to the fourth, and again, that is in ohms. All right, so moving into our second example. All right, so the second example here, we have which change decreases the resistance of a piece of copper wire. All right, so it tells us a material here, and we're going to look at all our answer choices to see if we can kind of use an equation in order to actually answer this more conceptual style question. So we have resistance. So we have resistance here. So put R down. It says the piece of a copper wire here. And if you look on the electricity portion of the reference table, in the bottom right hand corner, you have resistivities at 20 degrees Celsius. And that's where you have all different materials of wire, and copper is on there. So we're going to put down resistivity, which is the Greek letter rho. It looks like a P. What do we have now in the answer choices? So we have increase in the wire's length, so that's L. Decrease in the resistivity, which again is rho. Decrease in the wire's temperature, and decrease in the wire's diameter. All right, so diameter will have to do with the wire's area actually. So what we're going to do here is put A with that. And then an equation that actually works out with this is, if you look on the reference table, another one with resistance. The other one is for resistivity, so rho times length over area. So resistance equals rho times the length over the area of the wire. So now we're going to look at what would actually decrease the resistance of a piece of copper wire. So it says increase in the wire's length. So the wire's length in this equation is directly proportional to the resistance. So if I increase the length of the wire, I'm going to end up with a greater resistance. So A, not going to be the answer. Increase in the wire's resistivity, again, that is in the numerator of my equation, so it is directly proportional to my resistance. So if I increase the resistivity, the resistance also has to increase. So B goes away. C, decrease in the wire's temperature. We're going to come back to that in a second. It's not in the equation, but it's more of a conceptual idea. And then D, decrease in the wire's diameter. So if I decrease the diameter of the wire, my area is also going to end up decreasing. So if I decrease my area, it is inversely proportional to the resistance. If I decrease that number, my resistance will then go up. So this is also not the answer. Just by a process of elimination, C is going to be the answer. But the idea behind this, which we didn't have the equipment to actually touch on properly, but with the Ohm's Law lab, we could have figured this out. If you put a regular resistor versus a light bulb, the light bulb, as you actually increase the voltage through the light bulb, the resistance is actually going to increase. It's not going to actually obey Ohm's Law. So if I increase the temperature in the wire, same idea here, my resistance will actually increase. So if I decrease the wire's temperature, it's the opposite, obviously. If I'm increasing the temperature, the resistance increases. If I decrease the temperature, the resistance will also decrease in that situation. So our answer here is going to be answer choice C. You can either figure that out based on process of elimination. You don't have to know the idea that temperature increases. If temperature increases, the resistance increases. But if you know that idea, then you can pick out that answer right away. So answer choice C is my answer. So let's move into example number 3. All right, so example number 3 here, we have 20 joules of work is used to transfer 20 coulombs of charge through a 20 ohm resistor. The potential difference across the resistor is. So again, let's just write out everything we have, then we can match it up with an equation on our reference table. So we have if 20 joules of work, so we know that it's telling us that joules is work here. So we have here W equals 20 joules. Then this is used to transfer 20 coulombs of charge. So again, it directly tells us that coulombs is charge, and we look on the reference table and see that Q is equal to charge. So Q is equal to 20 coulombs through a 20 ohm resistor. So again, it's telling us that the unit for resistance is ohms. We look on the reference table for resistance, and that is R. So R equals 20 ohms. And then finally, it's asking us to find the potential difference across the resistor. So we have here that potential difference on the reference table. Again, we look for that. That is V, and that is what we are looking for. So look for an equation that is going to find us potential difference with either all of these variables or only some of them. So let's look for potential difference on a reference table. The first equation that's going to jump out to me, the third one down, is V equals W over Q. Do I have all of that here? I have work which is W, which is 20 joules, and I have charge, which is 20 coulombs. And I'm trying to find V, so I can use this equation, V equals W over Q. So let's just plug everything in now. We're looking for potential difference. That is V. W is 20 joules, and then the charge is 20 coulombs. So potential difference V is 20 joules over 20 coulombs. 20 over 20 is going to end up being 1. And our unit for voltage or potential difference is going to be just volts. So 1V is going to be my final answer here. Let's move into example number 4. This is example number 4, more of a conceptual question again. So a circuit consists of a resistor and a battery. Increasing the voltage of the battery while keeping the temperature of the circuit constant will result in an increase in. So what am I given here in this question that I can use with either an idea that I have or an equation that I have learned in order to actually answer this? So it says we have a resistor and a battery. A battery is something that supplies potential difference, and then it says increase in the voltage. So resistor is R. It then says voltage. We know voltage is V potential difference. What else do we have here maybe in the answer choices that we can end up using? A says current, so we'll have here I. And the rest of them is everything we've seen here before: resistance, current, and resistance, or current and resistance again. So what equation can we actually use in order to answer this question or an idea that we may have learned in a lab? So we have here R, V, and I. Look for an equation that involves all of these things. And I'm looking on the reference table on the left side there, and it's R equals V over I. So R equals V over I. So from here, I can then figure out what they're asking me in the question. So it says, while keeping the temperature of the circuit constant would result in an increase. So if I increase my voltage here, resistance is staying the same. What must also happen in order to keep resistance the same? So if my temperature is staying constant, that means my resistance is not changing. So I'm looking at the answer choices here, and I can see 2 already that I can get rid of because this B says resistance only. So again, resistance is not changing if I'm not changing the temperature at all. And then C has resistance in it as well, so that can be gotten rid of. So either we have D, where neither current or resistance change. So the resistance isn't changing, so something else has to change if voltage has to go up. So I'm looking really at answer choice A here, that the current only is going to change. And this makes somewhat sense. So let's kind of like plug in numbers here if you wanted to. So say if I doubled the voltage but I wanted to keep the resistance the same, the current would also have to double. This is something you also saw when you did the Ohm's Law lab. Whenever you when you created the graph based on that, wherever you had the data tables, as you increased voltage through the circuit that you created, the current also increased at the same exact rate, and you got a linear graph. So if I increase the voltage in the battery and no temperature change, my current must also increase at the same exact rate. So we're gonna have answer choice A here, current only. All right, so let's move into, so let's show this as well. This goes up. Let's move into number 5. All right, so example number 5 here, the total amount of electrical energy used by a 315 watt television during 30 minutes of operation is. All right, so again, let's see what we have here first. It says the total amount of electrical energy. So let's look at our reference table in electricity and try and find electrical energy. So on the right side here, I'm looking through everything that I have on the right, and it says towards the bottom, work, in parentheses, electrical energy. So that means I'm trying to find the work that is being done in this amount of time. So let's put here W equals question mark. All right, then it says used by a 315 watt television. It doesn't specifically tell me what this even is. But let's go back to our ideas and the units that we have here in both actually mechanics and electricity. So what is watts? Watts is the rate at which energy is used, or which work is done, and that is joules per second, which means if we know that work is joules, joules per second is actually power. So this is the power that is being used by the television. So we have here that P is equal to 315 watts. And this is during 30 minutes of operation. So we have here time equals 30 minutes. One thing that I see here already is time is in minutes, and we can't use minutes. We don't use minutes in here. SI unit for time is seconds. So before I even worry about any equation I'm going to use from this, I'm going to convert my time into seconds real quick. So I have here, I have 30 minutes. And in order to go from minutes into seconds, all I have to do here is multiply this, put 1 minute on the bottom because I wanted to cancel out minutes, and then figure out how many seconds are in 1 minute. We should know that 60 seconds are in 1 minute. So now let's just do the multiplication here. Minutes will end up canceling. We'll have 30 times 60, so 30 times 60 is going to be 1800 seconds. All right, so now we can look at an equation because now we have everything in the proper units, so 1800 seconds here. So let's look on the reference table for an equation that we have to find work, we have power, and we have time. So if I go all on the left side here, all the way to the bottom, I see that I have my equations for work. Work equals power times time. So let's write out this equation. So W equals P times T. Oops. All right, so again, work is power times time. Let's plug in what we have here. We're looking for work. We have the power that is 315 watts, and that is times our time, which is 1800 seconds. All right, so let's just plug this into our calculator, and we're going to end up with the total amount of electrical energy used in this time, or in better terms, the work done in this time. So we have here 315 watts times 1800 seconds, and that is going to give us a pretty big number. We are going to have here 567,000 joules. So again, if you want to make this into scientific notation, let's actually do that as well, just in case it ends up being a multiple choice question. So we have here 567,000. We have 6 digits before what would be a decimal there. What you're going to do here, it would be 5.67. So really 5.7 times 10. And again, we have 1, 2, 3, 4, 5, 6 digits before what would be a decimal. We subtract 1 from that, so 5.7 times 10 to the 5th, and that is joules. If you're ever unsure about a scientific notation situation, just plug it into your calculator and make sure it lines up with what you ended up actually getting. You don't want to get that wrong if you did everything else correct and you just didn't do the correct scientific notation. So let's just box this off here. And that is our final answer. So let's move into example number 6. All right, so example number 6 here. A little bit wordy, but it is more of a conceptual question again. We have a 1.5 volt AAA cell supplies 750 milliamperes of current through a flashlight bulb for 5 minutes, while a 1.5 volt C cell supplies 750 milliamperes of current through the same flashlight bulb for 20 minutes. Compared to the total charge transferred by the AAA cell through the bulb, the total charge transferred by the C cell through the bulb is. All right, so we're just comparing the C cell here to the AAA cell. So let's see what we are given. We're given voltage, so we'll put down here V, because we can use an equation to actually end up answering this. We are then given current, even though it's in milliamperes, it's still the same thing. So we have here current, and we have a time. So the time here for both of them. And then it says at the very end that compared to the total charge transferred, so that means we have Q. Again, all of these variables come from the right side of the reference table. Just pick out what we have there, and it says that's equal to it from there. All right, so let's figure out an equation that we can end up actually using in order to answer this question. So we're trying to find the total charge transferred, or the comparison of the two of those things. So I have voltage, I have current, I have time, and I have charge. Which equation can involve three of these things at the very least? I'm trying to look for charge. If I look on the reference table, charge is involved in a few equations, but it's involved in an equation with time and current, and that is current is equal to the change in charge over time. So we have here I equals change in Q over T. All right, so now we're going to compare two things. So how we typically do this is actually just plug in, we can actually just plug in the numbers here and figure this out based on this. So since they're in milliamperes, we're going to keep it as milliamperes because it's not really going to change much here. And we're not going to have to convert from milliamperes into amperes here. So we'll just plug everything in. So let's do our first scenario. So this is the AAA battery. So let's plug everything in. Q, if we do a little bit of algebra, is going to be equal to I times T. So current times time equals change in Q. So let's plug in our numbers here. We have 750 milliamperes. So let's plug in 750 MA times the time. And that is 5 minutes. Again, we don't need to convert anything here because we're not trying to find specific numbers. We're just trying to find a comparison. So we can just plug in 5 minutes here. It'll make our life easy. Change in Q. So let's multiply these two numbers together. So 750 milliamperes times 5 minutes. And that's going to be a number here, 3,750. And then the units for that, not really going to worry too much about that for right now, because again, we're not having to be specific. So that's our change in Q for the AAA battery. And for the C-cell battery, we're actually going to plug in our numbers again. So we have here 750 milliamperes times 20 minutes is equal to the change in charge. So we're going to multiply those two numbers together. So 750 times 20. You're going to end up with 15,000. Again, don't really worry about the units here because you're not trying to be specific. You're just comparing these two. And this will save you the most amount of time on a multiple choice question. You don't want to spend too much time, especially in a Regents situation. So let's just compare these two numbers. What we're going to do is divide them. So just do 15,000 over 3,750. So we'll do this and we'll figure out how much bigger this is. And you should end up with 4 here. So we should have 4 times as much charge is transferred through the C-cell battery than the AAA battery. So we should have answer choice D here is going to be the answer. Let's move into example number 7. All right, so number 7. We have a 3.5 meter length of wire with a cross-sectional area of 3.14 times 10 to the negative 6 meters squared is at 20 degrees Celsius. The current in the wire is 24 amperes when connected to a 1.50 volt source of potential difference. Calculate the resistivity of the wire. All right, so let's see what we are given here, and then we're going to figure out what we need to find. So first thing we are given here is a 3.5 meter length of wire. So we have here that length, if we look on the reference table, is going to be L, and that is 3.5 meters. And then we are given a cross-sectional area. So let's look in the reference table again. Find cross-sectional area is at the very top, and that is A. So that is equal to 3.14 times 10 to the negative 6, and that is meters squared. Again, with this, that's just the unit. For area, you're not actually squaring the number when you plug it into a calculation. And this is at 20 degrees Celsius, so this tells us on the reference table that our resistivities are valid. Alright, so the current in the wire is 24 amperes, so we're also given current. So look on the reference table again. What is current? That is I, so that is equal to 24 amperes. When connected to a 1.5 volt source of potential difference, again, find potential difference on the reference table. That is V, and that is 1.5 volts. And then we're being asked to find the resistivity of the wire. So let's look for resistivity on the reference table. Again, here we find it at the very bottom on the right side before parallel circuits, and that is rho. It looks like a P. Is rho is our question mark here. So let's figure out an equation with all of this. We might be missing something though as well, because if we're trying to find the resistivity of the wire, in that equation, if you look for the only equation that involves resistivity, it says that R equals rho times L over A. We don't have the resistance here. It did not give us the resistance. So R is also a question mark. So we're going to have to actually find that as well. So since we are missing two things in the equation for resistivity, we're going to have to find our resistance first as well. So is there an equation that we can find our resistance with that doesn't involve resistivity based on what we have here? So we have length, we have area, we have current, we have potential difference. We do not have resistivity, and we do not have resistance. An equation to actually find that resistance so we don't have two unknowns in the resistivity equation is going to be Ohm's law. If you look on the reference table, looking for an equation that has resistance, it is R equals V over I. So we have to find our resistance first with this and then plug it into the resistivity equation. So let's do this real quick. We have here looking for resistance, that is R. Our voltage V, that is 1.5 volts, or potential difference V, over our current, which is 24 amperes. All right, so plug this into our calculator, we're going to end up with our resistance, so 1.5 divided by 24 amperes, and our resistance is going to be 0.06, and we'll make it 3. So our resistance time with ohms as the unit there. If you do this in the math on your calculator, you're going to end up with 0.0625. We'll just round it off to 0.063 ohms. All right, so now we finally have our resistance. So now we should have enough in order to find our resistivity, because the only equation with resistivity on the reference table is R equals rho times L over A. And now we have the other three variables in order to find our resistivity. All right, so looking at this equation here, R equals rho times L over A. I'm just going to make my life a little bit easier right now and solve for rho without plugging in any numbers, because there's scientific notation. It gets a little bit messy with that. So let's solve for the algebra first and then plug in the numbers to get our answer. So in order to get rho by itself, that's our ultimate goal here, what are we going to do first? Rho is being currently multiplied by L and divided by A. So the first thing I'm going to tackle here is being divided by my area. In order to get rid of something that's being divided, you do the opposite and you multiply it on both sides of the equation. So we're going to multiply A on both sides of the equation here. And it is going to cancel on the right side, and we're going to be left with resistance times area equals rho times length. The last thing here is going to be getting the resistivity by itself. So in order to do that, it is being currently multiplied by the length of the wire. In order to get by itself, we do the opposite operation. And the opposite operation of multiplication is division. So we divide out length from both sides of the equation. And we're going to end up here with an equation that we can now use, which is R times the cross-sectional area over the length is equal to the resistivity rho. Alright, so let's plug in our numbers and we should end up with our answer here. So the resistance that we have is 0.063 ohms times the cross-sectional area, which is 3.14 times 10 to the negative 6 meters squared, all over the length, which is going to be 3.5 meters, is equal to resistivity rho. What I'm going to do here first, just so I can show all the steps, is multiply the top. So 0.063 times 3.14 times 10 to the negative 6. That's going to give me a value on the top here of 1.98 times 10 to the negative 7th, and that is going to be ohms times meters squared, all over 3.5 meters. And if this was a part 2 question, you don't have to show this step as well. You can just go from the first step that I have here with all the stuff plugged in and just have the answer. This is just for better clarification if you want to see where I was going with the math. So now we divide this, so 1.98 times 10 to the negative 7th. This is going to be divided by the length of the wire, which is 3.5 meters. So I should end up now with a resistivity of 5.66 times 10 to the negative 8th. And our units, when we have this, it's also on the reference table. We have ohms, and one of the meters will end up canceling out. So times meters equals the resistivity here. So this is our final answer. Alright, so this is probably the most difficult equation to work with because there's more variables than the other ones that we are going to end up using for the circuit basics, but this is going to be our final answer. I suggest doing the algebra beforehand if it ends up being a part 2 style question, because it makes it a little bit easier instead of jumbling around the scientific notation, moving it around with the numbers in it. Moving around with just the variables makes your life a tiny little bit easier. So let's move into our next example. Alright, so example number 8. We have, what is the current in a wire if 3.4 times 10 to the 19th electrons pass by a point in this wire every 60 seconds? Alright, so what do we have here first? It says, what is the current in the wire? So let's see what current is on the reference table once more. It's still I, so we have here that we are looking for the current I, and that is question mark. It says that 3.4 times 10 to the 19th electrons pass by a point in this wire every 60 seconds. Alright, so when it says electrons or protons, that just means this is the amount of elementary charges that are passing through the wire. So that is a type of charge, but we don't typically work in elementary charges, we typically work in coulombs. So let me write down here, Q equals 3.4 times 10 to the 19th E, and we're going to work with that in a second. And then it says every 60 seconds, so simply here we have time equals 60 seconds. So again, like I said, when we have charge, we typically work in coulombs and not elementary charges. So what you want to do with this is actually convert from elementary charges into coulombs, just like any other conversion, except we are given the conversion factors on our reference table. So let's convert from charge, elementary charges, into coulombs. So like any other conversion, we're going to write out the number. So 3.4 times 10 to the 19th E. And then what I'm going to do here, there's two ways of going about this. The way I'm going to go about this is going to see what one elementary charge is in coulombs. It makes my life a little bit easier here instead of using the amount of elementary charges for 1 coulomb. Alright, so if I look on the reference table, I see that 1 elementary charge, so I'm going to put that on the bottom because I want the elementary charges to be cancelled, is going to be equal to 1.6 times 10 to the negative 19th coulombs. Alright, so again, just like any other conversion, I have what I have originally on top and on the bottom because I want that to cancel out, and I'm being multiplied by my conversion factor here. So when I multiply these two together, elementary charges cancels out. I'm going to have 3.4 times 10 to the 19th times 1.6 times 10 to the negative 19th coulombs. So now I will be in coulombs. So 3.4 e to the 19th, or times 10 to the 19th, multiplied by 1.6 times 10 to the negative 19th. So multiplying these two numbers together, you are going to end up with a value of 5.44 coulombs. Alright, so now I have my charge in coulombs, and I'm going to look for an equation that involves everything that I have here. So I have current, that's what I'm looking for. Now I have my charge in the proper unit, and I have my time. So let's look at an equation that involves all of these things. I'm looking for current. I see current in a few equations, but the one that is most relevant to me right now is current is equal to change in charge over time. So let's just plug this in now. So current is equal to change in charge. Make that Q a little bit better. Over time. Alright, so current is what I'm looking for, so we keep that as I. The change in charge here is 5.44 coulombs over the time, which is 60 seconds. Alright, so let's plug this into our calculator and end up with our answer for current. So 5.44 coulombs divided by 60 seconds. And we're going to end up with our answer here as 0.09. And of course, the unit for this is going to be amperes, so capital A. And that is our final answer. All right, so let's move into example number 9. So example number 9 here, we have if the potential difference applied to a fixed resistance is doubled, the power dissipated by that resistance remains the same, doubles, halves, or quadruples. Again, we can use an equation in order to answer this question. Let's just see what we are given. We are given here a potential difference. So potential difference, V, on the reference table. A fixed resistance, look for resistance, that is R on the reference table. And it gives us the power dissipated. So we're given directly power. We don't have to decipher that electrical energy transformed is power. So we have here that P is power. Alright, so based on this right now, we are going to be able to figure out which equation we can use in order to actually find this and then figure out our answer. So let's look at power. Let's look for an equation that involves both potential difference and resistance. And we have at the very end here that P equals V squared over R. Alright, this is one of our law of one situations. So what I'm going to do here first is plug in 1 for everything. See that we're obviously going to have 1P because 1 squared is that. And then if I double what I'm doubling, which is going to be the potential difference, I'm going to see the difference between those two things. So let's look for our power. If I plug in 1 for my voltage, or potential difference, and plug in 1 for my resistance, I'm also then going to end up with 1P. Alright, so then, based on the law of ones, all I'm doing is changing whatever I'm being told to change in the question and comparing these two to each other. So it tells me that the potential difference is doubled, and we have a fixed resistance. So my resistance is not changing, but my potential difference is doubling. So from 1 now to 2 squared over 1. If we do everything here, 2 raised to the second is 4 over 1, and now I have 4P. So I should have it quadruples because at the beginning, before anything is changed, it is going to be 1 or whatever value I had, doesn't matter. If I then double that value, it then quadruples the power. So with this as well, an idea you can even use if you want to use Ohm's law to actually find this, it would be a much longer way to go about it. But my current would also double if my potential difference doubled, and I could use I squared times R, and you end up with the same exact value. But this is the easiest way to go. You don't have to worry about using this another form of the power equation or using another equation in our electricity portion of the reference table. So again, when we compare these, if I double that value, we're going to have 4 times the original value, so quadruples is our answer. So let's move into example number 10. All right, so example number 10 states that at 20 degrees Celsius, 4 conducting wires made of different materials have the same length and the same diameter. Which wire has the least resistance? All right, so it's given us a bunch of materials, so that's going to tip us off to where we're looking on the reference table as well. So again, look on the electricity portion of the reference table. You are then going to look at the bottom right hand corner. You're going to see that we have all different materials. Based on this now, we're going to see which of these has the least resistance. There's one kind of odd resistivity there, and it gives us in a weird scientific notation nichrome, which is 150 times 10 to the negative 8th, which is not a proper way to write scientific notation. So just to make this a proper comparison here, you have 150 times 10 to the negative 8th. It really becomes 1.5 times 10 to the negative 6th. So now that resistivity is bigger than everything else, so we don't have to really worry about it. So nichrome can actually go away. All right, so the rest of these. Let's look at our equation. And I'll explain again why nichrome goes away in a second. So let's look at the equation that we have involving all of this. So we have length, we have diameter. Diameter goes directly with area. It's asking us to find the least resistance, and it gives us these 4 conducting wires, which means we are working with resistivity in the situation because we have different materials. So the equation for this is R equals rho times L over A. So again, we look at this, resistivity is directly proportional to resistance. So with nichrome, I have the biggest resistivity. So that means that can have the least resistance. That's why it goes away. So let's look. So that's just a comparison of which one has the least resistivity of the other 3. So aluminum. Aluminum has 2.82 times 10 to the negative 8th for resistivity. Gold has 2.44 times 10 to the negative 8th. That's a little bit less. And then we have tungsten, which is 5.6 times 10 to the negative 8th. All right, so between gold and aluminum, aluminum is going to have a greater resistivity than gold is. So gold is going to be our answer for this. It has the least resistivity out of the 4 that are on the reference table. That's all that are being given here based on the reference table. We're just looking at the resistivity equation, seeing that this has the least resistivity out of all of them, and that means that is going to be your answer. All right, so let's move on to our next example. So what is the resistance at 20 degrees Celsius of a 2-meter length of tungsten wire with a cross-sectional area of 7.9 times 10 to the negative 7th meters squared? So again here, we are looking, the first thing we have here is resistance. Look at the reference table for what resistance is. That is R, and that is our question mark. It says that we are at 20 degrees Celsius, which means our resistivities on the reference table are valid. That is again in the bottom right hand corner. So we have then a 2-meter length of tungsten wire. We have here in the reference table length. If you look for that, that is L. That is the length of the conductor, and that is going to be 2 meters. And it says tungsten wire. So even though this doesn't give you a value outright, look on the reference table of something that says tungsten. And that's why it says 20 degrees Celsius. You look on the resistivities table in the bottom right hand corner of electricity, and you see that tungsten is 5.6 times 10 to the negative 8th. So that is going to be rho again. So resistivity on the reference table is the Greek letter rho. It looks like a P. And the value for tungsten there is going to be 5.6 times 10 to the negative 8th. And that is ohms times meters. It gives you the units on the table as well. Then it says we have a cross-sectional area of 7.9 times 10 to the negative 7th meters squared. So what is cross-sectional area? You look at the very top of the table, you see that that is A. And that value given to us is going to be 7.9 times 10 to the negative 7th meters squared. All right, so again, let's look for the equation that involves all of these values and then what we are trying to find. So we have resistance, and resistance is with two different equations. But for this situation, we are given the length, the resistivity, and the area. So that equation on the reference table, when we line it up with your variables, is going to be R is equal to rho times L over A. And we're looking for resistance, so we don't need to do any algebra beforehand. We're just going to plug in our numbers and figure out our answers. So we have here R is what we are looking for. We are given the resistivity based on the material of the wire from the reference table, so 5.6 times 10 to the negative 8th ohms times meters. That is then multiplied by, let me fix the 5 here. That is then multiplied by the length of the wire, and that is going to be 2 meters over the cross-sectional area, which is 7.9 times 10 to the negative 7th meters squared. All right, so from here, again, what I'm going to do just for clarification purposes is multiply the top, show that, and then divide it by the bottom. So resistance, starting off with this, 5.6 times 10 to the negative 8th. That is then multiplied by 2. And we are going to end up with, on top, 1.12 times 10 to the negative 7th. And that is going to end up giving us a unit here of ohms times meters squared. And this should end up making sense because we should only be left with ohms at the end of the day for our resistance. So we have down the bottom the cross-sectional area here, which is then going to be 7.9 times 10 to the negative 7th meters squared. So then we're going to just plug this into our calculator and make sure we divide them. So 1.12 times 10 to the negative 7th divided by 7.9 times 10 to the negative 7th meters squared. And we are going to end up with a resistance here of 0.14 ohms. That makes sense because we have meters squared on top, meters squared on the bottom. On the bottom, those cancel out. We are then left with ohms for our answer, or for our unit in the answer. So that is our resistance, 0.14 ohms. Let's move into our final example. All right, so the last example here, we have which physical quantity is correctly paired with its unit. This is a pretty difficult question for some people if you have trouble with units, or it could be a really simple question for people who have all their units pretty much memorized. So let's go through all of these and figure out which ones we can kind of take out first, based on what we know either from this unit or from units previously. So looking at A, we have power and watts times seconds. We know that power is the rate at which work is done or rate at which energy changes. So that is joules per second. It ends up becoming watts as the unit, so that's not going to be the correct answer there. Power should be watts, not watts times seconds, so A can go away. B, energy and newtons times seconds. So what is a Newton? All right, so Newton is mass times acceleration, so that's kilograms times meters per second squared, and then you'd have it times seconds again. So that's not going to end up being correct because when you look at something for energy, so let's look at any equations for energy from even previously in mechanics. So let's like bring up, say, PE equals mgh, right? So m is mass, that's kilograms. G is the acceleration due to gravity, that's meters per second squared. And then height is also then meters. So it wouldn't make sense for it to be newtons times seconds because then you'd end up with kilograms times meters per second, I believe, when it really should be kilograms times meters squared over seconds squared. So B is not going to be the correct answer. So that goes with B. C, electrical current in amperes per coulomb. Um, what we've been doing so far here and what we've learned is that electrical current is equal to amperes. So dividing that by coulombs doesn't make much sense. Even if you look at the equation for that, it wouldn't make much sense either because current is coulombs over time actually. That what creates the ampere there. So this one is not correct either. And then D, by process of elimination, is the answer. But we could also figure is how electrical potential difference and joules per coulomb. So let's look for the equation of electrical potential difference. And the one that you actually solve that way is the first thing in the equation on the reference table is V equals W over Q. So based on this in units, W is joules. So I'm not multiplying this by joules. I'm just saying that that is the unit for it. So let me just put this in like parentheses actually next to it. And again, I'm not multiplying by this. These are just the units I'm showing. That is joules over charge, which is coulombs. So joules per coulomb ends up being potential difference, which is voltage. So that's going to be my answer for this question. All right, so I hope these explanations were helpful, and see you guys in class.